Hello, everyone, and welcome to today's webinar on an evaluation of ultralight insulating panels for operable windows. I'm Andrea Silvestri with GSA Center for Emerging Building Technologies and the Green Proving Ground. Before we get started, I'm going to run through just a few webinar logistics. The webinar today will be in listen-only mode, and you may submit questions by using the Q&A button, which you'll find on the bottom of your screen. And you don't need to wait until the end of the presentations to submit your questions. In fact, we encourage you to submit your questions well in advance of the Q&A session. Today's webinar is being recorded and it will be shared. You can find presentation slides and recordings for all webinars on our webinar page at gsa.gov. And you can also access all webinar recordings on our YouTube channel. Today's webinar is based on an evaluation by the Pacific Northwest National Laboratory, and you can find the full report and summary documents on gsa.gov. And we'll also be posting links in the Zoom chat window. And a quick rundown of today's agenda. First, we'll have a short introduction to the opportunity for window retrofits from Aaron Lannon, the program manager for the Applied Innovation Learning Lab. Michael Meyer and Edward Louis from the Pacific Northwest National Laboratory will provide an overview of the evaluation and results. And we'll hear comments if our property manager can join us. We'll hear comments from Daniel Carroll, but we know that GSA property managers are often busy. So if he's not able to join us, Edward and Michael will be sharing that feedback. And we'll have a live Q&A at the end. And again, please put your questions there in the Q&A at the bottom of the screen. And with that, I'd like to turn it over to Aaron Lannon.
Thanks, Andrea. So we're really excited to talk to you about this technology validation. And if you go to the next slide, please. Today, we're really going to talk about how windows are a critical element of any building, and inefficient ones can negatively impact the building's comfort, energy bills, and carbon footprint. Window technology development, deployment, and adoption to increase the impact that high-performance windows can have on decarbonizing buildings is really important to GSA and a lot of the other CRE entities. And as you see here on this slide, 34% of commercial energy use is attributed to windows. So we'll go to the next slide. So why is this important? So GSA has a number of large goals in terms of what we're trying to do to support catalyzing clean energy and emergent technology through our federal portfolio. As many of you know, Executive Order 14057 is supporting goals by 2030 that include 100% carbon-free electricity for our portfolio and a 65% reduction of operational GHG baseline. And how can window technology help support GSA's broader goals that are outlined in the EO 14057 above? Again, windows can play a key role in building electrification efforts. By improving performance of windows, GSA can do more than just reduce air leakage. As we look to optimize the influence windows have on a building's thermal energy demands, we can look at how we can minimize sunlight on hot days and maximize it on cold days to reduce energy loss and usage. And so a lot of what we're going to be talking about today here with our partners from PNNL is really focusing on what we learned from this validation and how it could be used in different scenarios. So we'll have Edward Louis from PNNL up next to talk about the validation and a lot more detail about this technology.
Thank you. So yeah, thank you for an introduction, Aaron and Andrea. My name is Edward Louis, and I'll be presenting the research and findings from this project. This project looked to evaluate these ultralight insulating panels that are mounted on the interior side of primary windows. The design of this ultralight insulating panel strives to maintain the native operability of the primary window. And as Aaron said, when improving the performance of windows is super important. Windows have a very long life on buildings, but they are replacing the primary window is often extremely costly, extremely logistically challenging to do. So thus, even though we know that they are a thermal hole in the wall, doing something to improve and reduce that heat loss or heat gain through those windows is often very challenging because it is so expensive. So, everybody's looking towards how do we improve this thermal hole in the wall in a more logistically feasible manner, in a more cost-effective way. And so, this product is, as you will see, is another kind of feather in the cap of feathers that can help achieve that goal. And one thing to note is that even though windows have really long lives, particularly the earlier generation of windows, so windows that are already 25 to 30 plus years old, even if they're double pane or perhaps even triple pane, those early generation windows have seals that are probably starting to fail. And so as a result, the real world performance, even though you physically see double pane, the performance may not be at double pane performance anymore. Next slide. So here's a little bit of a more detailed photo of how this insulating panel works. It operates by attaching 4 corner adhesive tabs that have a kind of Velcro, or it's more like actually a mushroom head style Velcro surface on it. Those adhesive tabs are very clear, and they're mounted onto the interior glass surface first, and then this insulating panel snaps onto those mounting tabs to secure the insulating panel to the window. And then later, in the future slide, we'll see that the thickness of this panel is also quite thin, and so the clearances enable the window to remain natively operable, which can be really important for certain buildings that need it for that native operability for egress or for climate control. Next slide. So the material of this insulating panel is really thin. It's a 20 mil copolyester plastic. When you touch it, feel it's analogous to kind of the clamshell takeout box, clear takeout box type plastic. It's about that thickness, maybe just a tad thicker. The manufacturer, Wex Energy, makes 2 versions of this insulating panel. One that has a tint applied to it, and that tint reduces the solar heat gain, and it's intended for warmer climates where it's desirable to reduce solar heat gain and increase the insulating value of the glass surface of the window. This project tested the version of the product that's clear, and the clear version is designed for colder climates where it is desirable to maintain that solar heat gain to help reduce winter cooling needs. In the future, this manufacturer, it plans to make this product from recyclable materials. Currently, it's already made 100% in America. So in terms of sustainability, this product has good sustainability goals. Next slide. So here's kind of an edge view to show off, just how thin this product is. The high profile version that we tested creates a 0.5 inch gap between the panel and the window. Why 0.5 inch? That happens to be actually the ideal gap or airspace for air-filled insulating. So like the insulating panel creates a dead airspace between the primary glass and the insulating panel. And if that space is filled with air, the optimal gap space for reducing thermal losses or maximizing the insulating value of the panel is 0.5 inch. One of the cool things about this panel is that it mounts to the glass. And so if you have a operable sash and a fixed sash, they're oftentimes at different planes from a certain fixed plane. So by mounting the glass, each individual insulating panel is always optimized at that 0.5 inch gap. So that's quite nice. they also make a low profile version, which has a slightly suboptimal air gap, and that does affect the insulating value a little bit. But the low profile design is available because some windows need that low profile design in order to have the clearances necessary to maintain native operability. Next slide. So as I said, like the real goal in how do we improve the thermal performance of windows is to seek solutions that are actually ones that you can execute easily or economically, and some of that has to do with logistics. Okay, like many buildings are occupied, so they have furniture and people, and so it's if you need to transport something very large into the building, a occupied building can be very challenging to retrofit. And so one of the advantages of this technology is that it mounts onto the glass surface. And as you can see in the upper right picture, this particular window is actually comprised of multiple glass pieces that are smaller than the actual total window size. So what we call, in the window world, that's called multiple pieces of glass that have been munted or mullioned together. And so by attaching to the glass surface, each individual insulating panel can be smaller. And you saw on the previous slides, the adhesive tab and then snapping that panel into place. So it's a fairly easy install. It involves few tools. The GSA staff that did the install, they took them about 10 minutes per panel, and that includes, getting the panel to the right place, putting the adhesive tab, prepping the glass surface for the adhesive tab, etc. 10 minutes per panel. They made some comments that it's probably easier to install than other technologies because it is light and you can do it even when there's furniture around the window. And you see in the upper picture that there's like a sticker and like a bluish tint. So that's a protective film that the manufacturer has applied. And that sticker has like instructions on like which particular panel to place on which window. If the windows are all a little bit different size, then it's just like a map to make it easy to put the right one in the right place. Being smaller and lightweight, they can ship multiple panels per box, typically 10 per box, and that the overall weight of the box, even when there's 10 inside, is still light enough and of a size where it's easy to move by 1 or 2 people. Next slide. So here's some of the performance of this insulating panel. We have in the cold climate panel, both the manufacturers rated performance that they did with Intertek, a independent rating agency, and then also the measured values that, and we'll get into later a slide, how we measured in situ U values, and then the R values are just the reciprocal of the U values. And then the manufacturer's performance for the tinted panel that is designed for warmer climate is also shown in the lower part. Do note these values are based on the product attached to either a single pane window or an older double pane window that now has the performance close to that of a single pane window. So these are not the performance if you were to apply it to like a brand new double pane window. So keep that note in mind. We'll go to the next slide. So the test facility was the Federal Building and U.S. Courthouse in Eau Claire, Wisconsin. It's a historic building built in 1909, 37,000 square feet, listed historic places. The windows in this building were replaced in the 1980s with double pane windows, metal frame, and the double pane has a decent number of them. You can tell that the seals have failed. They're at certain times of the year, they do fog a little bit. So that's one of the kind of telltale signs that the seals have failed. This building is located in cold climates and zone 6A. Next slide. So in October 22, 75 insulation panels were installed. The building actually has quite a few different sizes of windows, resulting in 57 different sized insulating panels. The measurement and data was spanned 2021 to 2023. We have set up sensors to measure the in situ real world U value. In this case, on the left-hand side, we're measuring that U value with the insulating panel plus the primary window. And then on the right-hand side, we're measuring the U value of the original window without any treatment. Next slide. And here's the results of that in-field U value measurements. What we found is that the double pane air-filled windows have a U value around 1. That's kind of surprising because that's not normally what the U value of the double pane window is. But as we noted that, these windows are getting old and the seals are starting to fail. And when there's some moisture that gets in between the air-filled gap between the two panes of glass, the U value decreases quite dramatically. And so these double pane windows are in fact actually performing closer to single pane. But with the insulating panel attached, the improvement in the U value is about 52%. So great improvement. And so that's what we found. Next slide. This building also has a interesting building controls, and so it has a very aggressive nighttime setback. So the nighttime setback is into the upper 50 degrees, and so that's a pretty significant drop from your typical 72 during the day. And so that creates a very interesting natural experiment that we can look at. So we can look at how the rooms in the perimeter cool off and the rate of cooling off. And so what we found is that once the insulating panels were installed, the rooms cooled off slower because, well, the heat loss through the windows is slowed down. And so that decrease in the rate of cooling off was about 31% during the winter months. So very interesting. Next slide. We also found improvements in the interior glazing surface temperature. With the insulating panel, the interior glass surface temperature was warmer by about 7 degrees when it's 0 outside. And then on a day when it's -5 outside, the interior glazing surface with the insulating panel attached was warmer by about 8¼ degrees. And we can go to the next slide to kind of really also understand why this is important. So interior air is warm, and that warmer air also has higher humidity, and that humidity comes from, well, humans breathing, sweating, washing hands, and etc. Your coffee mug releasing humidity. And so that humidity will find the coldest surface in the room to condense. And the window glass surface is often the coldest surface in the room. And so if you can warm up that coldest surface, then there's a reduced chance of condensation. And that condensation, depending on what type of material is around the window, if it's wood, that can damage the wood finishes and wood trims. And so by reducing condensation around the window, you can improve durability. And sometimes if that condensation around the windows dwells for too long, you can actually get some mold. And so you might also have a reduction in mold around the window even by reducing condensation risk. And we found that to be the case from the warmed up window surface temperature. Next slide. And so how do these products look? One of the things that we found is that we found mixed results, and we weren't able to ask necessarily detailed questions from the occupants that took the survey on why they answered negatively or positively, but we can speculate. The test products included some new features that those new features, when they were delivering these insulating panels to our pilot test sites, were not in full production yet. So the pre-production versions were 3D printed, and the 3D printer could only make these elements using a kind of a milky white material. And so like the mid-span support for long edge length panels were 3D printed. So you can kind of see that tab in the upper right picture. And then also another kind of feature that's new was the cutout around window locks. And that was also 3D printed using milky white plastic. And so these contribute to kind of the, what's it called, a visual draw to the insulating panel that would not be there in a full production version. And speaking right now, these features are in full production now. So like if you were to buy a panel today, they would be made out of clear plastic. And so next slide, we can take a look at what the difference is in a full production version. So like in the case of a mid-span support, on the left-hand circle, you can see that you really don't see that mid-span support anymore. The manufacturer delivered a sample of the full production version midway through the research so that we can at least get one full production version of the panel to look at. And so it's a big change from the pre-production version. So the mixed, what's it called, aesthetic survey results might be improved if you were to, buy this panel today. Next slide. So we did have the instrumentation, and we collected utility bills to assess whole building energy use and before and after. But due to changes in occupancy and some construction that was going on in the building, it turns out that the energy savings was of the insulating panel was lost in some of the other things going on in the building. So we also used energy modeling to assess the energy savings of this product. We did the modeling using the DOE medium-sized office building model, specifically the version that is designed to model the prototypical building constructed pre-1980. Next slide. So the results is a range, and the reason why there's a range is because one is due to climate zone, and then two is it depends on what the primary window is. Is your primary window single pane or double pane? And then if your primary window is metal framed or non-metal framed, that makes a difference, because if you recall, this technology mounts the glass surface, interior glass surface of the window. So as a result, it really doesn't do anything for the window frame. So if your window frame is made out of metal, obviously metal conducts heat really well. So then your energy savings will be less. And then also we did the energy modeling with different percent frame area. So obviously some windows have really fat frames, and then other windows have really thin profiled frames. And so then the percentage of the glass surface that remains that can be treated by this product is different. And so that also affects the whole building energy savings. So accounting for these different factors, the whole building energy savings is between 2 and 7% is what we found. And that seems like a really low number, and it kind of is. But one thing to note also is that the medium office building model makes exterior envelope improvements look not as significant, because it's a building that has a lot of internal volume. And so then the surface area to internal volume is not that great. Whereas like in like a residential home where, the internal volume is a lot less compared to the surface area, then exterior surface area treatments will result in greater energy savings. So keep that in mind. Next slide. And so we looked at native current cost effectiveness. using the current material cost and then also the current GSA electricity and gas rates, and then what the savings would look like, and then use that to calculate simple payback. Interesting, what we found is that in the modeling, the warmer climate has favorable savings to investment ratios because the tint on that product reduces the solar heat gain and therefore makes a significant improvement in the air conditioning loads, in addition to the insulating value that it provides. In moderate climates that really don't get a whole lot of heating and cooling load, then the product really struggles to perform well in the savings to investment ratio. And in cold climates, we hit a savings investment ratio on average of right at 1. Next slide. So we also looked at, okay, well, what is the cost in the different climate zones, the electricity price would need to be, or what the gas price would need to be, or what the product, how cheap would the product need to be in order to achieve a savings to investment ratio of 1. And so here's the table for that. And we found that like if you had a cost for gas that's ranging from like $3 per $3.18 per MMBTU, and in certain climate zones it needs to be as much as $21.53 in order to be cost effective. And then for cold climates, the panels need to be as cheap as $8 per square foot, or in warmer climates as cheap as $17 per square foot to be cost effective. So that's so another way to look at it if you want that data. Next slide. So some of the lessons learned is in moderate climates, when there's not a lot of heating and cooling load, you need some really inexpensive envelope treatments in order to be cost effective. We also the manufacturer of this product is also quite concerned about mounting their insulating product to windows that have aftermarket tint films applied to the interior glass surface already. So the concern is that the adhesive tab in the corner, if it was mounted to the film, then perhaps the weight of the panel will over years pull off of the glass surface, not necessarily because the tab is not able to hold onto the glass, but because there's that tint in between, and it's actually the adhesive between the tint and the glass that's failing, leading to then the insulating panel failing. We did not observe that in this research project. We had a very small number of windows that had tint film applied. An effort was made to remove a tiny corner of tint off of like the first window that had tint film applied. It was very difficult to remove that tint film off the glass, so indicating in this particular test building that the tint was very stuck onto the window. And so we did one, and then there were a few more windows that had tint film on it, and so due to how difficult it was to remove the tiny corner of tint in the first window, the adhesive tab was actually just placed onto the tint film in like 2 or 3 more windows. And during the entire test period, those windows had no problem with delamination of the tint, even though the adhesive tab. But it is a concern. The product manufacturer does not condone applying this adhesive tab onto tint films just because they can't warranty it. And again, this product, one of the hallmark or selling features is the ability to maintain the Windows operability. In this case, the test building really does not operate the windows at all. And so we did not actually prioritize picking a profile that would result in clearances to maintain native operability. So in our test case, the insulating panels were just thick enough that you would have to unsnap the top insulating panel in order to operate the windows. But again, like I said, in this GSA test building, the windows are really extremely rarely operated. But there's a low profile version that would enable native operability. Next slide. So some other best practices is site-specific evaluation. So as I said in the kind of beginning when I started my presentation, there is a plethora of insulating window technologies that can be applied either to the interior window or exterior of the window to improve the thermal performance. And we really need to improve the thermal performance of windows. So the solution is likely going to be, a Mod Podge or, different sites using different window improvement technologies due to either the different characteristics of the windows. Some sites might have many windows that have multiple glass lights that have been mullioned and munted together. Others have really leaky operable sashes that, need to be, the air leakage at that meeting rail needs to be reduced. Some sites may not have any problems with moving a very large insulating panel that covers the whole window from frame edge to frame edge, versus others, they may have extreme difficulty getting such a insulating panel into place. So it's very site specific. One thing that we had discussions with the manufacturer about is, well, if we took the measurements and the measurements are not correct and resulting in a insulating panel that doesn't fit, who has to pay for the remake of that insulating panel? Well, through that discussion, the result was that it's best to get the vendor to take the measurements. And so then if there happens to be an incorrect size, then they would be responsible for remaking the insulating panel. That's probably a good idea, not just with this manufacturer, but in general. Of course, if you're going to mount anything to the window, then it's important to clean the windows first. And so we did put that into the logistics of this project. And this particular product does not seal edge to edge from window frame to window frame. And so air infiltration that often occurs, obviously, through like the operable sash. So if the meeting rails or the operable sliding portions of the window are leaking air in a significant way, then this product doesn't really address that issue. And then also noise tends to come through the window through those gaps, or the when you have air leaks, noise can come through the air leaks in the most significant way. And so if air infiltration and noise is a major issue with your existing windows, then perhaps consider a window technology that mounts from frame edge to frame edge, or the drywall surface to drywall surface of the window opening. But even then, it's like, okay, well, it really depends. Like, okay, how big is your window? Can you even get a insulating panel that big through the door and up the staircase and into the room that it needs to go into? So the best window insulating improvement technology is the one that you can actually execute, and not just say, come to the conclusion you can't do it and therefore leave the window as is for God knows how much longer, because we have really near future targets to reduce the energy usage of our buildings. So we really need to do something. And then if operability isn't really important, that might also trigger the move to a different technology that has higher thermal performance. And those insulating other technology do exist if operability isn't of primary importance. Next slide. So some other recommendations is that this particular technology, because it doesn't have like especially the cold climate version that is clear, it does not impact the street look of the building. So if you were to install a insulating panel technology that has a tint or like some sort of low-E coating, you can potentially affect the curb appeal of the building, and that might run into historic regulation issues. So it's one of those trade-offs again. When you have a tint, then it's good that changes your solar heat gain. If you have a low-E coating, that improves the thermal performance of the insulating panel. But can you get that passed through your historic building what's it called, committee? I don't know. So this particular technology is in the cold climate one, doesn't change this street facade of the building. It's particularly good for single pane or older double pane windows with non-metal frames or thermally broken aluminum frames, because, like I said, it treats the glass surface only, and you get the most improvement to the glass surface when it's single pane or double pane, and that has started to fail and therefore operates closer to single pane performance. It's also really good for windows that have multiple pieces of glass mullioned and munted together. So like in this picture, edge to edge on this window is over 5 feet. And then in height, it's like over 8 feet tall. So could you imagine trying to get an insulating panel that covers the window from frame edge to frame edge and try to logistically get that up the staircase and into the room? It could be very, very difficult. Whereas if you just treat in each individual glass panel, then that's much easier to do. The manufacturer currently has a size limit for the individual glass panes, which is 4 feet by 6 feet. And we did not run into any glass on this building that we tested that exceeded that size. So that's a pretty good working range. Next slide. And so, let's see, do we have...
Hi, Edward. I'll take over the rest of the presentation for the last few slides, if that's okay.
Oh, perfect.
That's great.
Okay.
Thank you, Michael. Yeah, our building manager, Daniel, wasn't able to join us. So Michael Meyer, the other researcher on the project, will be presenting these slides to talk a little bit more about on-the-ground feedback. Thank you, Michael.
Thank you. And I just want to say thank you to the audience. Some of your questions are really thought-provoking, and they're coming in, and I appreciate them. One of the people asked about heaters, because it is Wisconsin, and I'm not going to lie, I visited in December when it was -10 degrees outside in Eau Claire. And yes, there were some heaters in the building. We did notice a reduction. Now, let's be honest, building operators don't always like heaters for the safety reasons, but they sometimes sneak their way into offices. But the building operators did notice a reduction in space heaters after the insulation panel. So that was a question. I appreciate that. Also, there were some people who wore just blankets over the laps, and that was reduced. So overall, I'm going to touch base on the insulation and how it worked. Field measurements were a little bit of a challenge. The vendor did come out to help take the actual window measurements. That's important. You really need to measure to get everything right so they can cut the panels. It's helpful to do that. And then this from a GSA point of view, the vendor intended this to be something that anyone could do, but obviously GSA wants to limit their risk and try to put that on a vendor to take the measurements or a contractor, and so that's how that was performed. Cleaning was also imperative. We did discuss earlier in the presentation the film, but also just in general, because you're adhering something to the solid face of the glass, it's important to clean it before you attach the adherents. So those are two things that you should factor in your installation. Next slide, please. So overall, as we discussed, the view didn't really change. Obviously, these are relatively very clear. The visual transmission is quite high on them. So the view didn't change at all. We did receive some feedback. We did administer a survey to the building occupants. They did move around in the building during the construction process. during our evaluation period, there was also construction in the building, and that caused some people to be relocated for their new offices. So some of their views did change because of that. But the big comment that overall we saw was the corner pieces where that you're actually attaching it, and then also some of those pieces where the spacers, which are shown in this picture here. And then there's the bolt I included there at the last end. Fewer space heaters were on site after post-window installation. Next slide, please. Yeah, and this was, now some of these windows are very large and quite heavy to open, but they still like the idea to be able to operate them, though we did try to inquire how often they were operated, and it is very low. But because of the way the two panels worked, the two windows worked, the top panel, as shown in this picture, had to be removed so that the lower window could be opened. That was considered a hindrance by a couple of people in the building, just because they would have liked to have been able to open it how they wanted that. It would have been, with small reduction in savings, the lower profile insert may have been the better option to go with, and then that could allow the windows to pass, but that wasn't evaluated at this time. Next slide, please. Again, really the idea is, like, if you ask someone, do you want to open your windows, they're always going to say yes. The idea of having some fresh air. And again, the picture in this, he's cleaning off the glass where we adhered one of the meters. They're quite heavy, at least in this office. Not all the windows are the same size, but these windows are large. But they like the idea to open it. And that is the value of the technology. Taking off the panel in that picture, other than the ladder, took all of about 2 minutes. And you can still slide it up with attachments on the window that holds the panel in place. So it does allow for flexibility if you do want to open those windows. But overall, it's still allowed for the operability. Next slide, please. And that kind of sums up just the experience by the building operators and the building staff. And now we have about 15 minutes to address some of your questions that you've been providing. And this is the exterior facade of it. I'll take this time while we're queuing up the questions. Someone asked about historic preservation, and I know Edward mentioned it as well. Because this panel is mounted to the inside, the SHPO office was supportive of it, also because it's not permanent. Other than taking a putty knife to scrape off where the attachments hold the panel in the window, it relatively can go back to its original form. Now, these windows were installed in the 1980s, even though this is a 1930s building, so the windows have been changed at one time already. But overall, SHPO was supportive because it did not affect the exterior appearance, and within the interior side, it had a relatively limited permanent effect, and it could be always reverted back to the original shell.
Great. Thank you, Michael. And we have, as Michael said, thanks for all your questions. There were a lot of great questions. We may not get through all of them, and we'll, if not, we'll also be following up with a follow-up Q&A. So with that, I'll jump into the first question. How does this panel protect against condensation?
Yeah, so the panel has edge seals, and then by warming up the interior surface of the glazing, then the condensation happens when the moisture reaches a cold enough surface to reach dew point. And so by warming up the interior surface, that the air touches primarily, because now the surface that is the original primary window is now protected from the what's it called, the air movement that brings that moisture to that glass surface. You have a warmer new surface, the interior surface, and so then that warmer new surface it will reduce the amount of condensation risk.
This is related. It's not clear how this product creates a dead airspace. Could you explain how it seals around the perimeter of the device to maintain that half-inch gap and creates a seal along that perimeter?
Yeah, is it possible to jump back to the slide where we look? Let's see, it would be slide 14.
And Michael, if you want to jump in as well, because we have a lot of questions to get through, so we probably need to have fairly quick responses.
Yeah. So, anyways, it's got a basically a it's a piece of plastic. The way it's folded, it when you put the adhesive tab and it snaps together, then there's basically pressure from the adhesive tab to hold that gasket against the primer window. Michael, is that a good description?
Yeah, there's no actual sealing. It's just friction and pressure. I think it's a great answer.
Great, thank you. And Michael, would you recommend this technology for fixed windows?
I think it's an option for a fixed window. Obviously, its primary benefit argument is for operable windows because it's designed to work for that. There are many options to consider for fixed windows and that you could consider. So I'm not saying sure, but I would say it's in the canopy or options list. But its real prime focus is really maintaining that operability.
What's the lifespan of these panels?
I think, I mean, it's plastic. I don't actually remember documentation, but I would put it over 15 to 18 years. We did receive a question from GSA staff. We did not evaluate it in I grew up in a warm climate, Phoenix. We didn't evaluate it for sun, those type of things. But we can follow up in notes, but I believe at least 15 years.
Thank you. Were the U values you shared earlier in the presentation only center of glass?
So the measured U values are center of glass U values. We did not have heat flux sensors to measure edge of glass performance. The manufacturer's claims for the U value improvements were done according to ASTM standards, standard practice for how to measure U value in the laboratory.
Great, thank you. And what's the margin of error in calculating the savings? There was a comment, it seems close to the total of the savings.
Michael, do you want to speak to
that? So it
calculates,
yeah, so it's a fair question. It is close to the savings. I mean, ultimately, because of on-site, so certain measurements were accurate and they had higher levels of savings. But when we start talking about the 2 to 7% building savings, those were modeled. And so I think that comment is fair. I think that unfortunately, the quick answer is it's going to depend on which measurement we talk about. The modeling will have larger degrees of inaccuracy versus some of the other metering that we did, such as the direct measurement against adjacency windows. But it is fair to say that some of them were definitely close to the margin of error. Yes.
Great, thank you. In the energy savings slide, the window configuration is listed as 2 panes. Is the double an IGU and the single a single sheet of glass in profile?
Correct. Yes. The double pane would be an IGU.
Great. Do we know if the panel affects GSA bomb blast or other glazing safety requirements where applicable?
So we did not evaluate it. Oh, go ahead.
Oh, so yeah, we did have like 1 or 2 windows in this building that were bomb blast rated primary windows, and so since there is no testing that was ever done to evaluate how this insulating panel, if it were to be attached to a bomb blast primary window, would perform, the decision was made to just skip that one particular window.
A question about the cost-effective prices and where the figures based per square foot. I think the answer is yes.
Yeah, there's a fair amount of things in there, but yes, square foot was included.
Okay, perfect. Do we know how the savings from these panels compare to replacing a single glazed window with a double glazed IGU?
Well, the thermal performance improvement is probably going to be much better if you replace the primary window, but in previous research that have been done on replacing the primary window, the problem is not the energy savings, it's just the huge upfront cost. And so it takes literally forever sometimes for the savings to work down that upfront cost.
Let's see, what was the numerical solar heat gain coefficient change in the favorable example that was mentioned for the tinted versions of this interior panel over single and double glazing? Because typically there's not much solar heat gain improvement for interior absorbing layers.
Yeah, so the primary window in the manufacturer used in the warm climate test is a clear glass window, and then it's the solar heat gain change when they applied the insulating panel with the tint. I don't understand the question about usually aftermarket applications don't change the solar heat gain coefficient very much. Like your typical window tint will change the solar heat gain very significantly.
And just a confirmation, is that 52% insulating savings that you mentioned, is it for the whole window or just the glass?
That was on the U value measurement change, so that is center of glass improvement.
Okay, great. What did you use to determine that some of the double pane units had failed? Typically, when double panes fail, you will see condensation issues, other signs of failure between the glass.
So there were a good number of IGUs in this building where at certain times of the year, the building facility management staff did note that they observed condensation in between the panes of glass. So that's one indication that we know that at least some of the windows have failed to the point that enough moisture has entered the IGU to create that effect. Others that had less moisture ingress into the IGU did not have any particular day where fogging in between the panes of glass were observable, but generally you don't have a window with seal failures. There's different levels of seal failure and different levels of moisture that enter. It depends on how big that failure is and how long has that failure been in place.
Do we know of how the panels might perform during a seismic event? Is the glass tempered, and how breakable is it? What's the mode of failure? We may have to get back, but if one of you has any input.
Yeah, so these are, like I said, plastic insulating panels, so they will not break or crack, but certainly that doesn't mean the primary window won't break or crack. So if the primary window is not tempered, then it will break into big shards, and then if it is tempered, it'll break into smaller, safer pieces. But I would imagine that the primary mode of failure will be the primary window failing in a seismic event.
If these panels fell, I mean, we're talking maybe 2-3 pounds on you, and very limited plastic. It's the actual window itself, which is not evaluated, would be the failure point.
The report said that some of the units fell off and had to be reinstalled. Can you speak to that?
I'll handle that one, Edward.
Okay.
Yeah, thank you for reading the report. I wouldn't say it fell off. I would say, again, how these work are 4 attachments, 1 per each corner. There were a number, more than 10, but less than 100 of corner attachments that separated. So essentially, if you were looking at the picture, one of the corners was kind of free floating, where it had separated from the piece of glass it was adhered to. This was raised. The vendor came back and discovered and changed, I believe, the adherence material, the actual, I'm not going to say epoxy, but something like that they attached to it, and they reattached it, and all of those windows, when I was there in May, were back on, and those type of things. So they did come loose, and they were addressed.
Great. Do you think operability is considered more important than air infiltration or draft protection?
I think both are important, but it depends. That's more of a user decision, I think, on what is your priority.
Great. Michael, did you want to say something about that? No.
I just, if you have a fire, if you have a fire access window, you're going to need the operability. If energy is your only thing you're caring about, obviously air filtration is more important, but it is often a balance.
Great. Can you speak to the process, to the overall cost per square foot of the technology? And I know that is included in the report and the summary documents.
Yeah, I'll try to figure. It's a little vague, so I'm just thinking out loud. So the vendor provided a cost per square foot. then we added a cost. That was for the material costs. We added a cost for some labor to actually install them and do that. And then for cost effectiveness, we calculated the energy savings. In this chart, and you can see what the simple payback was and the savings to investment ratio. We have a separate chart in this table where we actually kind of reverse engineered it and said, if you were paying today's gas prices and electricity prices to get a savings to investment ratio of 1, what the panel costs would have to change to. We did look at both initial cost and a more kind of standardized cost from the vendor. One of the challenges at the site were so many different window configurations that it did increase the cost of the panels because they were so many different variations. But in a standardized run, after they'd upscaled, their pricing would have been slightly different.
Thank you. And this slide shows the assumptions of $1.6 a square foot for installation and $16 for the warm panel and $9 for the cold weather panel. Do we know whether the clear mounting points will degrade or discolor over time and need replacement?
We did not do long-term testing. As you saw in the research period, it's only like a year, so we don't have that data. The manufacturer can maybe speak to that if they're on this call. If not, we can get back to you by email.
Great. I think we'll respond to that in our follow-up Q&A. Were there any thermal or imaging of the treated windows pre and post?
Yes, we did do some thermal imaging, and they did show on the thermal imaging a much warmer surface.
How was the film on this project removed by GSA staff?
So are you talking about the blue film? The blue protective film is just easily, it's like any type of like packaging.
This is the applied film.
No, they're talking about the window, the post window laminate film. Unfortunately, I wish Dan was actually able to answer this question. I think it was a putty knife to remove, and once the sheet had come off in pieces, then they cleaned the window.
Great. Will cleaning agents damage the surface and reduce visibility over time?
So the manufacturer has instructions for like the type of chemical to use to clean this, and it's the typical like non-ammonia based window cleaning solutions, and they will not damage the product.
Okay, I think this just last couple questions. So if the window U value went down after the seal failure, how does the system improve the U value so much since it is likewise not sealed?
So the window after the seal failure, so at this point, then you're just talking about adding more layers of dead air space, and then it's the dead air space that improves the U value. In a traditional IGU, it's even if it's air filled, it's dry desiccated air that is in between the panes of glass that really gives air filled IGUs the good U value it has, and if it has low E coatings on top of that, then again that really improves the performance. But once the seals have failed and it's no longer dry desiccated air, you have moisture inside, then the convective elements and potentially even like infiltration, exfiltration, depending if there's 2 points of failure in that seal. All those things contribute to the reduction in performance of the primary window.
Great. Well, thank you, Edward, and thank you, Michael and Aaron, and to all the attendees for your great questions. So we're at time. As we mentioned, we will be sharing both a copy of the presentation, a copy of the recording, and the kind of the top answers to the Q&A, and we'll follow up with any outstanding questions. So again, we appreciate all your time. Thank you so much for joining us.